You're listening to Sovereign Radio. I'm your host, Chango and Change, and I'm here with Ismael, the founder of Lagrange. Welcome back to the show.
Thank you so much for having me, Chango.
You were here last year as well, and I was interviewing you, and a lot has changed in Lagrange. Tell me about it.
Yeah, so the interview last year was one of our favorite things we did at Modular Summit, and fortunately we're here again and excited to be back. So last year we talked a lot about kind of the underlying proving systems and proof constructions that Lagrange was designing and leveraging as we were working to commercialize what we thought of as a new attempt to scale blockchains. Since then, we've iterated on the product, iterated on the proving systems. We've launched in production one of the first proving networks in the crypto space. We're very fortunate to have a large number of marquee operators such as Coinbase, Kraken, OKX participating in our network and generating our proofs, and are very fortunate to have integrated with many of the top DeFi protocols in the space.
To give our audience some context, can you explain what a prover network is and what these institutions that you've just listed offer for the prover network?
Yeah, so a prover network can be thought of as a decentralized group of provers who are responsible for generating zero-knowledge proofs upon request. And so at our core, Lagrange focuses on ZK coprocessing, a scalability paradigm for blockchains. And within our ZK coprocessing requirements, we have the need to generate a large number of zero-knowledge proofs for the applications that we integrate with. So our prover network are participants whose responsibility it is to compute these proofs upon request that allows us to guarantee liveness of proofs that are delivered to on-chain applications. And so the operators that I listed are folks who are participating now in that proof generation process.
Right. And to what end are they making proofs on these networks for?
Yeah. So at our core, Lagrange focuses on a scalability paradigm called ZK coprocessing. And what ZK coprocessing is a way to allow applications on existing blockchains to scale the types of computation that they can access. For the last 10 years, we've been asking the same question in crypto, which is, how do we scale blockchains? And the approaches that most people have taken was building faster L1s, faster consensus, more expressive execution environments, or going horizontal or vertical in terms of trying to scale L2s and L3s. And this has created a plethora of issues when we think of the fragmentation of state, the fragmentation of liquidity, and then all of the problems that interop between all of these spaces. What a coprocessor is fundamentally is a way to scale existing applications on existing blockchains to allow them to use proofs in order to access more computation. So an application on Ethereum today can request a proof from Lagrange's network and receive a proof of some computation over the state of Ethereum that's delivered back at some future point. If it wants to be able to do a big loop or some big intensive computation over the state of Ethereum, it doesn't need to do it in its contract. It can simply request a proof of that and verify it later. And this means that where the applications exist today actually can scale, and they don't need to just pull themselves out and move to new execution environments and chains.
That's amazing. And in terms of this prover network, what medium does it reside on? Is it another chain itself, or is there some kind of off-chain computation happening? What does it look like?
Yeah, so our prover network now is deployed on top of EigenLayer. And there are...
As an ABS?
As an ABS, yeah. And so the operators of our provers have restaked Ethereum that they have as collateral behind their performance. And in the event that they don't generate zero-knowledge proofs within their allotted SLAs, they receive an economic penalty, either in the form of slashing or non-payment. And so it sort of resides as a secondary network or a middleware on top of Ethereum, whose responsibility it is to compute proofs of computation for Ethereum, Ethereum L2s, and even other execution environments that might not be Ethereum aligned.
So as an operator, for example, I'm Coinbase.
Yeah.
What is it that I'm running exactly to make these proofs?
You're running a node that matches the requirement set that's required to generate a certain type of proof within the network, either queries or pre-processing or really any of the kind of ways we stratify workloads and proof loads. And you then run the relevant circuits and you generate the proofs of the computation that you requested from the network.
Okay, so would this AVS module, what kind of data actually goes on the AVS module and why does it need to exist?
Yeah, that's a really good question. So I think to take a step back, one of the very interesting things about zero-knowledge proofs is that they are a fantastic tool for guaranteeing the safety of a computation. If you ask me the result of some mathematical equation, I can prove to you that I run that equation correctly with the inputs and that here's the result. But if you request me to provide you that information, the proof of it, there's no guarantee that I provide it for you on time. There's no guarantee that the liveness of the computation or the liveness of the proof are in fact delivered. And so this is where networks and prover networks become just so valuable. Because while you can guarantee safety from proofs, you can't guarantee liveness. And so on top of our prover network, we're able to make sure that when you request a proof, that proof is delivered back on time. So within the AVS, they download the relevant circuits, and when requested, there's an auction process within the network, and nodes bid for the capacity to generate proofs. And if they win, they have a time frame to generate that proof, and then they generate that and return it back. And so because of that, we're able to guarantee, advantage pricing, and that there will always be the proofs delivered on time because there is a plurality of network actors who are directionally incentivized to perform correctly.
Mm-hmm. So what is the incentive for these provers to provide the ZK proof?
Mm-hmm. Fees and tokens.
Fees and tokens.
The best things in crypto.
Fees and tokens of the networks that they are providing proofs for?
Yeah, so whenever you request a proof from the network, there is an imperative to compensate the network for the cost of generating that proof. Mm-hmm. It's obviously dynamic pricing depending on the throughput of the network. We can think of that like gas on an L1 or L2, but you can think of it like proof gas on the prover network. And you request that, you pay the fee, and then that fee is dispersed internally into the network to compensate folks who have generated proofs.
Got it. And does this network offer services for archival data?
So it can prove computation over any point of data on any chain. So it could be data that's stored in an archival node, or it could be data that's in the current state towards the head of the chain. The main thing it does simply is be able to assign a heterogeneous set of computations and proofs across these nodes, and then be able to coalesce and combine the results back and serve them on chain.
All that being said, what sorts of applications emerge from using this prover network?
Yeah, so I remember last year we were talking about something that Lagrange had called ZK MapReduce, or a way that we can prove MapReduce computation over on-chain data. We've since evolved that, and we had a recent paper we published called Trees, which is an updatable batch proof that supports MapReduce style computation.
Sorry, why is it called Trees?
It's recursive arguments on top of Merkle trees. So if we think of Verkle trees, Merkle trees, Reckel trees. And so it uses recursive snarks to define computation on top of Merkle trees.
Okay.
And so it has a number of interesting properties within it. The first being this concept of updatability and logarithmic time, which means you can change the data that you're computing over without having to regenerate the whole computation from scratch, which is great for blockchains where the majority of storage data doesn't change from block to block. And also, it has the capacity for us to prove arbitrary MapReduce computation over top of the data. And we've since taken that core construction, we've generalized that. We have a new paper coming out very soon that we call Perseus, which is a form of verifiable SQL through decomposition. It's very similar to a ZKVM, but it basically takes SQL, turns it into MapReduce style computations, and overlays that on top of our vector commitment. And so we've taken some of these kind of core cryptographic primitives that our team have developed and refined, and we've instantiated these in new ways to hopefully be able to deliver new application types to users. And a lot of the application types we see, to your original question, apologies for rambling on a little bit, but are personalization based, which is how do I take the result of your activities on chain and be able to develop an on-chain experience or an on-chain application that is aware of your prior interactions with it.
Okay. Can you make it more concrete for the listener? Personalization based. It sounds like you have user level view of whatever chain data they're making on whatever transactions they're making on chain, and for the user to be able to do something with it in a fast and scalable way.
Yeah. So the one of the big questions that we're able to answer with this type of scalability solution is compute over historical data, which is, you have a bunch of data in the blockchain that's provable with respect to the most recent block, any historical transaction, any historical receipt, any historical storage slot, and you want to be able to compute over that and verify the result of that computation in your application. And so this is useful for things like reward-bearing contracts, like Sushi MasterChef standards on most EVM chains. It's useful for volatility, real volatility instead of applied volatility. It's useful for funding rate for options protocols. It's useful for personalization in terms of how do I make sure this application is aware of your prior activity. Like if you've traded on a centralized exchange, you get volume-based discounts or volume-based perks. Or it's useful for GambleFi if you have ever gambled at a large casino and you have a certain tier of the amount of money you've lost. They usually give you rebates. But the on-chain applications that we build usually lack the capacity to have these types of features because they don't have access to this computation.
Yeah.
And so those are the types of things that we work on.
Yeah. Interesting. Is this ready for production now such that, because there's lots of projects that have point systems, right? And the point systems are only aware of their activity starting from the start of the point system, which is not a long historical timeline. But if they wanted to access some whale or individuals who've been around degenning for a long time and trying to tap into those communities, then they would probably benefit from something like this.
Yeah, that's a fantastic question. And so points programs are actually a use case we've been very frequently asked. If we look at a lot of the modern DeFi points programs, they're based on two heuristics, which is, have you provided liquidity into some application for a continuous period of time? And often have you provided a concentrated liquidity position on UniV3 that was in range for some period of time? So basically, have you provided liquidity and have you been able to provide both sides of a swap? And both of these things are basically assessing user activity for a continuous interval. And to your point, that's something this type of computation is very useful for. This type of proofs very useful for.
Right. So that being said, it's obvious that this prover system supports Ethereum and likely the rest of the EVM ecosystem. Yeah. Is there a plan to expand to beyond that?
Yeah, so, in the theme of Modular Day, we are very excited and are working with a number of modular teams. These types of scalability solutions, we believe, are universally applicable to any blockchain that wants more throughput or wants awareness of historical state. And that includes anything in the modular ecosystem. In terms of Cosmos ecosystem, we have that on our roadmap. Because I have a tremendous amount of respect for Cosmos builders, and actually the start of my career in crypto was in SF, where the Cosmos was a very central point in the community.
Excellent. Just to wrap up, can you give a highlight reel of your talk at Modular Summit?
Yeah.
High level elevator pitch.
Yeah, it digs into detail on a number of the points I've touched on today. How does the prover network work? How do the incentives work? How does the mechanism design work? How does the proving systems work? How does the vector commitments we're talking about work? And teasing a little bit how the verifiable SQL through decomposition, the new approach to proving query-based computational blockchain data, how that functions. It's really, we think of ZK coprocessing as a new scalability paradigm. The same way that we saw rollups emerge several years ago, I think we're seeing the early inception of coprocessing emerging on major blockchains. And we have a very unique approach to this. And in our talk, we presented a very detailed amount of information on exactly how our approach works and some of the benefits we believe it can deliver.
Very exciting. I'm excited to hear about your talk. And if you haven't heard it yet, do tune in to the Modular Summit talks, where Ismael is giving in-depth account of the prover system. And we're going to have Ismael back on Interchain FM, which is my own Cosmos-related podcast, to go into a deeper dive. And I hope you enjoyed this highlight reel. Thank you. Thank you for coming on.
Thanks so much.